Right, in this lecture video, I will be covering 6.4 metallic bond. And now when we started this chapter, we talked about different types of bonds, covalent versus ionic, and how covalent, there's nonpolar and polar covalent bonds. And we did electronegativities, and that segued us into Lewis structures and drawing Lewis structures for covalent compounds. And then we drew Lewis structures for ionic compounds and discussed ionic bonding. And so now this is kind of the third broad category of bonding, which is called metallic bonding. And I'm going to basically discuss why metals make such great conductors, and why they are shiny, and why they can conduct electricity. And everything pretty much reflects back to this property of highly mobile valence electrons. And you don't see this mobility in molecular compounds, okay? In molecular compounds, those valence electrons are localized in electron pair bonds between neutral atoms. They are assigned to one or the other. You know, they're being shared equally. But here, they are not really like held in place, especially like in ionic compounds where they are held in place. They're bound. So let's get to it. So in a metal, the vacant orbitals in an atom's outer energy levels tend to overlap. Okay, and because of this overlappage, the outer electrons roam freely throughout the entire metal. And when this happens, we say that the electrons are delocalized. They don't belong to any one atom, but they tend to move freely throughout the network of these empty atomic orbitals. So here we have this overlappage right here, okay? Where with semiconductors, it's a small gap. And so some of them may still be able to conduct electricity because the gap is small enough, and insulators do not. So to give you a visual concept, here are the nuclei, and these are the electrons that don't really, necessarily belong to this atom per se, but they're just kind of floating around through the overlappage of these outer energy levels. Okay, so we call this the sea of electrons. Okay, and they're kind of packed together in a crystalline structure, but again, mobile. So I have this video. I'll just see if it plays.
The outer electrons in metals are able to move a lot more freely than electrons in nonmetals and metalloids. Partially empty energy levels offer multiple positions for any given electron. Since outer energy levels of adjacent atoms are relatively close together, electrons in metals can also move from one atom to another. The result is metallic bonding. The positive metal ions remain in relatively fixed positions, while the negative electrons are free to move about. This creates bonds extending through the metal in all directions and leads to many of the observed properties of metals.
So here's another diagram of the electron C model, and how we have these positive ions from the metals and the electron cloud that doesn't really belong to any one metal ion in particular, but just floating around, and the overlappage of those valence. Why do I keep forgetting that word? Outer energy level. So as a result, we end up with metallic bonding that results from the attraction between these metal atoms and the surrounding sea of the electrons. And this goes in all directions, okay, all directions. And because of that all directionality, we tend to see metals as malleable and ductile. So some metallic properties. First off, electrical conductivity. They allow current to be passed through because of these electrons. Thermal conductivity, okay, very similar to electrical, but now we have the heat being transferred from one to the other because they're so closely packed together, and so heat, heats some atoms, and then they pass on the vibrations. They move faster, so metals make great conductors. Malleability, the ability to be hammered or beaten into thin sheets, and then ductility is the ability to be drawn into wire. So malleability, thin sheets, ductility, thin wire. Okay, so here's my metal rod, and I can force it into this die to create my wire. And here's my malleability, where I can hammer it into thin sheets. And you can see that even though, like, if I apply force to this row of positive ions, it doesn't break the bond. Now, notice that with ionic crystals, okay, now opposites attract, okay, negative charge, negative charge, alternated in this crystal lattice structure. When I apply a force and that negative meets with another negative, then we have repulsion that occurs. And that is why ionics, okay, tend to be brittle, and that crystal lattice structure will break. Okay, and then metals are shiny. Okay, and I wanted to look to see why. It says that because of the freedom of electrons to move in a network of metal, it accounts for high electrical and thermal conductivity characteristics of all metals. In addition, metals are both strong absorbers and reflectors of light. Because they contain many orbitals separated by extremely small energy differences, metals can absorb a wide range of light frequencies, and the absorption of light results in the excitation of the metal atoms' electrons to higher energy levels, and then they fall back, emit an energy in the form of light at a frequency similar to the absorbed. And so this is why we see this metallic appearance or luster of metal surfaces. So light, hits the metal, excites these electrons. The electrons travel to an outer energy level, and then they fall back, re-emit light at that frequency that it absorbed, and that's why we see metals as shiny. So yeah, here it is. So strong absorbers and reflectors of light. They contain many orbitals separated by small energy differences. They can absorb a wide range of frequencies, leads to the excitation of those electrons, and then they will fall back, giving metal its shiny luster. So again, throughout this chapter, we've discussed metallic bonding, ionic bonding with the metal bonded to a non-metal, positive, negative ions, and then the electrons being transferred. And with covalent, the sharing of electrons, and it could be equally or unequally. Okay, so just make sure you know some properties of each kind with our metals. They're shiny, ductile, malleable, ionic, crystalline lattice structure, brittle, can conduct electricity in a molten state, and covalent can be a gas or non-metal, but the sharing of electrons, and so on and so forth. So that does it for 6-4 metallic bonding.